So we spent a lot of time in the previous video talking about Johnston's Jeep Jug Kits and Becerra's Bronco Bonanza, and those were discrete random variables. We had countable numbers of each. Now, the last example that we're going to talk about to finish up random variables is a continuous random variable. So I'll set it up, I'll walk you through the exact same type of calculations. Again, the focus is on staying organized and what each of these values mean, and then interpreting our answer in context. So suppose Longquan's used car dealership runs autos through a two-stage process to get them ready to sell. Makes sense. When you have a used car, you want to fix it up, you want to make it look pretty before you put it on the lot. So the mechanical checkup costs $50 per hour and takes an average of 90 minutes with a standard deviation of 15 minutes. So we have our, let's say, our expected value or our average for mechanical is 90 minutes. And then they talk about hours. So it's 1.5 hours is 90 minutes. And our standard deviation, so I'm going to say our standard deviation of m is, what did they say, 15 minutes, which is a quarter of an hour. These are in hours because I want to be able to use the dollar amount. The appearance, prep, wash, polish, etc., costs $6 per hour and takes an average, so let's call that A, an average of 60 minutes or 1 hour with a standard deviation of appearance with 5 minutes. So that's 1/12, I think. 1/12 is 0.08 hours. What are the mean and standard deviations of the total time spent on mechanical prepping? Okay, so we have these, and we want to find the total. So the total, would you say the total, just in general, is the amount of mechanical work plus all of the polish and cleanup that they have to do? Well, if we're calling each of these a random variable, we have to figure out what are the mean and standard deviations of the total time spent on mechanical and appearance prepping a car. This is where this is not a discrete variable. Time is not discrete because we can have everything in between. So giving a standard deviation suggests we believe that the two phases of the process are independent, and that is the key thing. One mechanical doesn't necessarily mean you have a lot of cleanup to do. A lot of cleanup that you do doesn't mean that you have a lot of mechanical work to do. We can't be sure that is true, but let's make this assumption anyways. And by making this assumption, now it allows us to do a bunch of these calculations. We want to know the mean and standard deviation of total time spent preparing a car. We believe the two phases of the process are independent, so we add the variances. Now note, these two values that I highlighted, these standard deviations, are not variance. Variance of our total time is going to be the squares of each of these. Okay, so let m be our mechanical time and a be our appearance time, and let t be our total time. We want to know the total is equal to the mechanical plus the appearance for each car. We know that expected values, you just add the expected value for each. So we would expect to have 150 minutes if we just take 90 plus 60. Or we could say 1.5 plus 1, which is 2.5 hours, would be our expected value in time. With variances, and knowing that variances add, we first have to square the standard deviations. So the first one was 15 minutes for the mechanical work was our standard deviation, so we square that. We square 5, we add those up, we get 250 minutes, and we get 15.8. Note, this is not 15 plus 5 or 20 minutes. The standard deviations don't add, the variances add, because variance, since they are squares, is like the Pythagorean theorem. Just remember, something squared plus something squared. So we expect the total preparation to be 2.5 hours, or 150 minutes, with a standard deviation of about 15.8 minutes. Again, we could convert that to hours, and we will in just a second. So I hope that work matches. Our expected values we just add, but we add the variances, not the standard deviations. Okay, so again, our setup with long quants. What are the mean and standard deviation of the total cost to prepare our car? Okay, so total cost is factoring in the hours worked, which is why it's been key that we calculated all of these in terms of hours. So if we let M be mechanical time and A be appearance time, then our total cost to fix up these used cars is going to be $50 times how long it takes for our mechanical plus $6 times the appearance work. So we have our expected value is 1.5 and our standard deviation is 0.25. Our expected value is 1 for appearance and the standard deviation is 0.1 hours or 5 minutes. For appearance. So now we are finding the total cost, and so we are going to multiply each of those expected values in hours because units need to be in hours. Let's say hours to do $50 an hour. So what we're going to do is 50 times M plus 6 times the appearance. Well, we know that this is just 50 times 1.5 plus 6 times 1, which gives us $81. Now with variances, again, variances add. And so what we have to do is we're going to multiply 50 squared times our variance of the mechanical and 6 squared times our variance. And so what we had was 50 squared times 0.25 squared plus 6 squared times 0.0833 squared, which gives us $156, which is the variance of our total cost. Now, it's not asking for the variance. We want the standard deviation. So the standard deviation for the total cost is going to be the square root, which is $12.51. Note, if it costs you $81 and then your standard deviation you would call is this, 156, that means one standard deviation would be $156 away. That doesn't make sense. It's going to be smaller. So we expect the total preparation cost to average $81 with a standard deviation of $12.51. Again, I'm going to keep noting this. Variances add. Only this time it was with a scalar, so we had to square that as well. So nearly everything we have learned about discrete random variables is true about continuous random variables as well. When two independent continuous random variables have normal models, so does their sum or difference. So we can use that fact to apply normal probabilities to questions about sum or difference of independent random variables. And since we know time is this continuous random variable and not discrete, when it asks what is the probability that it will take longer to do appearance prep than the mechanical checkup? Well, the only way to answer this question is assuming that the phases of each process is independent and can be described by a normal model. So I want you to think, before we do this, does that seem reasonable? Does mechanical work versus the appearance fee for a used car seem independent? If we're good with that assumption, the next question goes, how can we determine if appearance takes longer than mechanical? So what we would look for here is if one takes longer than the other, we're looking for the difference between the expected values. And in fact, if appearance was bigger, or the amount of time it took for the appearance work is longer than the mechanical work, then the expected value would be negative. So if appearance takes longer than the difference between the time it takes for mechanical work minus the appearance time it takes is going to be negative. And so what we're going to do is we're going to subtract those two expected values. So to calculate the probability that it will take longer to do the appearance than mechanical work, we need to know the mean and standard deviation of the difference in time spent on each, which we know. The two phases of the process are independent, so the variances add. Variances always add even if we're subtracting. We'll subtract the expected values, but again, because of the squaring operation, everything becomes positive. Hence, we add them. With those assumptions, we can create a new distribution. So let D for difference be mechanical minus appearance. And so what we do is we take our expected value of each, and we're just going to subtract those. So it's 90 minus 60 in our given information, our average and average. So we have an average of 30 minutes would be our new model's mean. This would be our mean. To find the variance of the difference between these two, we're subtracting the mechanical and the appearance time, but we are adding variances. So that'd be 15 squared plus 5 squared, which is 250 minutes. Again, variances add. To find the standard deviation, we take the square root. It's the same as what we had before. Now we have enough information to create our normal model. And so when we create our normal model, we have our mean of 30 minutes and our standard deviation of 15.8 minutes. I want to know, where is this negative? Well, okay, so there's two ways of thinking about this. You can either say the z-score of getting lower than 0, because that's the only time that I don't know how to calculate under. The mean is not like 30 minutes. I want the difference to be negative. So I want the difference, or the z-score, to be at 0. So what I do is 0, which is the score I want, minus our mean, 30 minutes, over 15.8, I get negative 1.899. I want to know, given our standard normal model, again, with our mean of 30, or expected value of 30 minutes, and our standard deviation of 15.8 minutes, I want to know what's the probability I'm lower than that. Because if I'm lower than that, then the appearance took longer than the mechanical work. So I need to go over to my calculator, pull up a new calculator. I'm going to do two calculations for you just to prove a point. So first, our z-score, 0 minus our mean over our standard deviation, which is 15.8. I get negative 1.8973. I want to know what's the probability I'm below there, so I'm going to hit Menu, Statistics, Distributions, Normal CDF, Cumulative Density Function. And I want everything below all the way up to negative 1.899. I've standardized this with a z-score, so it's from 0 to 1. I hit Enter, and I see that I have a roughly 2.87% chance of having the appearance work take longer than mechanical work. So we expect mechanical work to take less time than the appearance, about 2.88% of the time. Notice we're interpreting that answer in context. Okay, so to wrap this all up, do not forget, variances of independent random variables add. Standard deviations do not. Don't forget, variances of independent random variables add, even when you're looking at the difference between them. And lastly, don't forget, variances of independent random variables add. Standard deviations do not. So that takes us into random variables. The last chapter, chapter 17 for unit 4, is on probability models. So let's practice these. I know it takes a little bit of work, but it's just a new way of looking at what we learned with our normal models in chapter 6. So I'll see you in chapter 17, Falcons.